We are surrounded by computers every single day, right? They're in our pockets, on our desks, everywhere. But have you ever really stopped and wondered how they actually work? At their core, they're just a bunch of on and off switches. So let's break down how that ridiculously simple idea powers our entire world. Because when you strip everything else away, that's it. At the most fundamental level, that is all a computer really gets. It's a machine built on a simple two-state idea: on or off. So the real question is, how do you get from that, from a simple switch flipping on and off, to everything we do, streaming movies, sending rockets into space, all of it? The answer is actually surprisingly elegant. The whole secret, the magic trick, starts with the one thing every computer needs: electricity. Let's dig into how that physical power gets turned into actual information. Okay, this right here is the bridge between the physical world and the digital one. It's so clever. Engineers basically decided, let's make a rule. The absence of an electrical current on a wire, we'll call that the number 0. And the presence of a current? Yep, that's the number 1. That's it. That is the foundational trick. Every single piece of information inside a computer is physically represented by this simple state. So if your only building blocks are a 0 and a 1, you're gonna need a language that only uses those two symbols. And that's exactly what we have. It's the universal language of computers: binary. You know, we humans think in what's called decimal or base 10. Makes sense, we have 10 fingers, so we use 10 digits, 0 through 9. Computers, though, they work in binary or base 2. They only have 2 digits to play with, 0 and 1. Everything has to be built from just those 2. So how does that really work? Well, let's take a number we all know, like 9. When a computer needs to represent the idea of 9, it translates it into its own language. And in binary, the number 9 becomes this sequence: 1, 0, 0, 1. It's a completely different way of counting, but it represents the exact same value. And here is where it gets kind of mind-blowing. This simple system isn't just for numbers. Letters, colors, sounds, even the tiny individual pixels that make up this very screen, all of it can be broken down and represented by long, unique strings of just 1s and 0s. It's an incredibly powerful alphabet. Okay, so the computer has a language, but how does it think or make decisions with it? This is where we have to meet the computer's brain cells. They're called logic gates. A logic gate is a microscopic electronic circuit. Just think of it as a tiny decision maker. It takes in one or more electrical signals, our 1s and 0s, and then it produces a single output, a 1 or a 0, based on a very simple, unchangeable rule. Let's look at one of the most basic types, the AND gate. As you can see, its rule is simple. It will only output a 1 if input A and input B are both 1. In every other situation, the output is a 0. It's a very strict gatekeeper. Now let's look at its more lenient cousin, the OR gate. This gate's rule is different. It will output a 1 if input A or input B is a 1. It doesn't care if it's 1 or both. As long as at least one signal is a 1, the output is a 1. And this is the perfect way to think about them. Each gate is making just one tiny logical yes or no decision. But when you combine millions or even billions of these simple little brain cells, something incredible starts to happen. So we have the language binary, and we have the brain cells, the logic gates. Now for the aha moment where we see how they combine to do something we all recognize, like simple math. So here's the big question, right? How do you get from these simple on-off rules to actually calculating the sum of two numbers? Well, the answer lies in a clever combination of the logic gates we just met. This is the workhorse of computer arithmetic. It's a special circuit called a full adder. It's designed to do one thing perfectly: add 3 single bits together. It takes a bit from one number, a bit from a second number, and a carryover bit from the previous calculation. It then outputs the result, which is the sum bit, and a new carryover bit for the next column. So the most crucial point is this. This little full adder circuit, built from just a handful of those and OR type gates, is the fundamental Lego brick. Every single mathematical calculation your computer performs, no matter how complex, is built using this one simple, repeatable block. Now let's zoom out and see how this one Lego brick builds the entire castle, because it is all about scale. And the principle is so simple. You just scale it up. If you want to add 2 8-bit numbers, you just chain 8 of these adder circuits together. To add 64-bit numbers, you chain 64 of them. By linking millions of these simple adders, a computer can perform any mathematical operation you can think of: addition, subtraction, multiplication, all at just unbelievable speeds. And how many are we talking about? The scale is just staggering. A logic gate is built from a few tiny electronic switches called transistors. A single modern computer chip can have over 25 billion of them, each one ready to perform its simple calculation in a fraction of a nanosecond. And that's really the ultimate takeaway. Whether you're editing a video, playing a game, or designing a building, it all boils down to the same thing: billions of incredibly simple yes or no decisions, happening so fast they create the illusion of complex intelligence. So that leaves us with a final thought. If the immense complexity of our digital world is fundamentally built on a simple binary choice, what does that mean for the problems we can solve in the future? What's next?